Let us discuss frames and machines. Our objective is to draw a free body diagram of a frame and machine and its members, also to determine the forces acting at the joints and supports of a frame or a machine. Of course, in the process, I'm going to introduce you to the differences between the frames and machines. Our activities include reading quiz and discuss some of the applications, how we can actually analyze a frame / a machine, concept quiz, group problem solving, and attention quiz. An example of a machine and a frame right next to each other is given here. As you can see, this machine consists of different members, member AB, BC, CD, DE, and EF as it is shown here. Let's take a look at a reading quiz. What are the differences between frames and machine and trusses? So the question is, frames and machines are different as compared to trusses since they have blank, only two force members, only multi-force members, at least one multi-force member, and at least one two-force member. The difference between trusses and frames and machines are actually the in their members, and that is in the case of a frame and machine, they should have at least one multi-force member. So the answer C is the correct answer here. Forces common to any two contacting members act with blank on the other member. This is reading quiz number 2. Forces common to any two contacting members act with blank on the other member. The correct answer is A. Forces common to any two contacting members act with blank on the other, act equal magnitudes but opposite sense on the other. This is according to the principles of statics, and it should not be really something new to you. Let's take a look at some of the applications. Frames are commonly used to support various external loads. This is like a scrap yard in this case, lifting some of some stuff, whatever that is, difficult to tell. But this is used to lift multiple members of a truss. It has different connecting elements here. As you can see down here, they're like more than one, so you can connect them to different parts of a truss and actually lift them up in case of a huge trusses and other types of members. So that's seems to be one of the applications. So how is a frame different than a truss? In order to be able to design a frame, of course, we need to know the forces first. So we do the analysis. Note that in this kind of analysis, we assume pretty much, in most cases, dimensionless width of the members, and that is good enough for our calculations and for our static purposes. Some more applications of the machines here are shown. They are also similar to frames. However, they are used in a variety of applications. The difference between machine, trusses, and frames is that machines are having a few, at least one or more moving parts, and both of these machines demonstrate that. Both the excavator here, that's short, it's a mechanical. It's shown, it has the arms as the way you see it, and they're all attached by hydraulic actuators. One here, one here, and one here, and of course there's an operator sitting inside the little cabin and operate the machine. This is a simpler machine. Again, there are moving parts, grabbing. It's a simple tool, as you can see, and they're connected at this point with a pin, and then you can pretty much screw and unscrew different types of bolts much easier than you can do it by hand. So this is another example of a machine. How can you determine the loads at the joints and supports? Well, we need to analyze them, and we need to take a closer look at them to see how we can actually analyze. So, by definition, frames and machines are two common types of structures that have at least one multi-force member. Again, I repeat, they should have at least one multi-force member. So they're not like two force members, like in the case of a truss element. An example of a machine, and an example an example of a frame, an example of a machine. They're shown here. Frames are usually stationary and support the external loads. However, machines contain moving parts, at least one, and are designed to alter the effect of forces. So you can imagine analysis of a machine which would be much more involved and complicated than analysis of a frame, than analysis of a truss. How can we analyze a frame or a machine? What are the steps that we need to take for analyzing a frame or machine? An example of a frame is given here. First, we would draw a free body diagram of the frame or machine and its members as necessary. An example is given here in this particular figure. First, we draw a free body diagram and try to pretty much digest the machine to the best we can. After doing so, we would identify any two force members, forces on contacting surfaces, and these are usually between a pin and a member. In that case, they're equal, but they're opposite in direction. And thirdly, for a joint with more than two members or an external force, we better draw a free body diagram of the pin to make sure that we are doing everything correctly. As you can see, there's a pin here at point B. We separate that, and the assumption is the force of member AB is actually pushing on this pin. As such, when we separate it, just below the pin B, you would see an F sub AB, and just above the point above the pin, you would see F sub AB. They are equal in magnitude, but opposite in direction. They exhibit an action-reaction type of a behavior. And then, secondly, in order to analyze the frame or a machine, we would develop a strategy to apply the equations of equilibrium to solve for the unknown. So the challenge here is with the available equations of equilibrium, we would be able to solve some of the problems that are more complicated but still determinate systems. The problems are going to be challenging, of course, because there are more unknowns, and frames and machines require more practice and more closer look at them to make sure we can understand them well. So let's take a look at an example. In this example, given the frame supports an external load and moment as shown, find. So this was given. Then find the horizontal and vertical components of the pin reactions at C and the magnitude of reaction at B. So the first thing is we would like to calculate the horizontal and vertical component of the pin reactions at C at this point, and also the magnitude of the reaction at B. So it's very important to first see what the problem is asking. There's a load applied here, 800 meter, that's a downward in the y direction, and there's also a moment of 800 Newton meter applied at this point right here. So the plan is we would draw the free body diagram of the um, frame member BC. Then we would apply the equations of equilibrium and solve for the unknowns at B and C. The reason we pick this part of the frame is because that's where we try to determine the unknowns, and it looks simpler, and this is probably require more consideration. That's why we pick this member. So we're going to look at the free body diagram of this member. Remember, we pretty much take this portion BC, we separate it from the rest of the structure and find an equivalent system that represents the real behavior of the structure. The most important thing here is F sub B, F sub AB, the reaction of AB. It applies in an angle. Again, when this force is being applied, you would see that this angle would represent best the reaction of the pin at point B. We would also show the supports reactions C as C sub X and C sub Y in the X and Y direction, assuming that this is X. Of course, this is a straight line, and this is Y in that direction. Okay? Okay. Then we will show the external forces, the 400 Newton and 800 Newton meter on the structure. The distances, of course, would be represented. This is the free body diagram of member BC. So as such, AB is a two-force member. Remember the way we identified a two-force member. They're connected at the two ends, and only two forces applied to them. Even though there's a moment applied at this point, that moment doesn't translate to AB because there's a pin at B. So AB is a two-force member. Equation of equilibrium, a summation of moment about point C, assuming the counterclockwise is a positive direction, would be written out as such here. F sub AB sine of 45 times 1. Let's take a look at summation of moment about point C using this free body diagram. There are three forces that are causing a moment about point C. And that is the 400 Newton force, and that would be multiplied by the moment arm, which is 2 meters, and that will be the moment as a result of 400 Newton. There is an 800 Newton meter, which is a pure moment by itself. That we are going to just write that out. Consider the pluses here as well, assuming that the counterclockwise direction is positive for the moment. And there are two components of F sub AB, and that would both of them cause the rotation, would cause produce moment about point C. And that is F sub AB. One is in the X direction, and F sub AB, the other one is the Y direction. The moment arc for one of them is 1 meter, for the other one is 3 meters, and that's how it is being shown here. This is the X component, so I put an X over it, and this is the Y component. I put a Y. This is Y, and this is X. There's only one unknown here. Sine of 45, cosine of 45 is known. And as such, we would go ahead and calculate F sub AB as 1131 Newton. Then we would take the summation of forces in the X direction to calculate C sub X, knowing that this force would be in the Y direction, and this one would be in the X direction. Knowing the force in the X direction and C sub X, we would actually take the summation of forces. This is the X component of F sub AB. So this is F sub AB X, and as such, C sub X would be 800 Newton. Then we take the summation of forces in the Y direction, considering that there is a 400 Newton force applied in the y direction. Note that here we did not include the 800 Newton meter moment, since we are just taking the summation of forces and not the moment. As such, minus c sub y plus 1131 cosine of 45 degrees minus 400 would be 0. As such, c sub y would be calculated at 400 Newton. So we calculated f sub ab, c sub x, and c sub y, and that is really what we needed to calculate. So the problem is pretty much complete at this stage, and we find the solution to the problem. Let's take a look at a concept quiz. Concept quiz number 1. The figures show a frame and its free body diagrams. If an additional couple moment is applied at C, then how will you change the free body diagram of member BC at B? So the free body diagram is shown. If an additional couple applied at C at this particular point, then how would we change the free body diagram of member BC at B? So if we have a couple applied here, how would that change the free body diagram of member BC at this particular point B? And there will be no change. Still one force F sub AB at B. We will have two forces B sub X and B sub Y at B. C will have two forces and a moment at B, and D we will add one moment at B. Well, even though we can apply a moment at C, and we are looking at the external forces, this is a pin at B. That's the key here. As such, the moment will not be transferred to B, so it doesn't really change. We will still have one force F sub AB at B. It's important to realize. And again, this is the free body diagram, not the magnitude of the force at B, F sub AB. The magnitude would be different. However, if the moment is applied right at C, over the pin versus over C, that would be different. If there's another member that pretty much connects to this machine at C, or this frame at C, and then things would have been a little bit different. But the moment is applied at C, and that's what the problem really asks for. So the second concept quiz is presented here. If the figures show a frame and its free body diagrams, if an additional force is applied at D, then how will you change the free body diagram of member BC at B? Again, the force is this time applied at D. As such, it's going to have the effect, it's going to change the two forces B sub X and B sub Y at B, because simply we're talking about B, and the force is applied right at D, and then it's going to affect the forces that are applied at B. So this is a good demonstration. So the correct answer is B. So this is a good demonstration to see how the location of the applied force or moment can or cannot or may not change the free body diagram or reactions at some other points on the frame or along the frame. Let's take a look at a group problem. As you know, we call these group problems because we go over them together and they are more involved. Given a frame supports a 50 kilogram cylinder, as shown here, this is the 50 kilogram cylinder, so we put a 50 here. This is a cylinder of 50 kilograms, so this is 50. The reaction that the pin exert on the frame at A and D is what we would like to find out. So there are reactions, there are pins here. One is in both directions, these two directions. At D, we are going to have the same thing. and we would like to find out what those reactions are. So we are going to draw the free body diagram of member ABC. Then we're going to draw the free body diagram of member CD, because without drawing a free body diagram for a member CD, it's very difficult to carry on the calculations. And we would apply the equations of equilibrium to each free body diagram to solve for the unknowns, for the 6 unknowns, then we would find strategies to solve for the unknowns much faster in a much more efficient way. So let's take a look at the free body diagrams of member ABC and CD. For member ABC, we produce the member here with the red forces shown as the external and internal reactions for the pin at these points. As you can see, at C sub Y and C sub X and C, we have 3 of them. One is the reaction of the pulley itself, the force that the pulley produces and exerts on the frame in 2 directions. The other one is the weight of the cylinder, that's shown here in blue, and that is causing the force. So that's due to the 50 kilogram cylinder. We need to multiply that by the acceleration of gravity, 9.81, to be able to calculate the forces in Newton. Also, there would be another one. Think about if you cut this from here, there would also be another reaction right here at that moment where you cut the weight. So there's one here due to the bearing, due to the load of the cylinder, and there's another one in this direction. Do these 2 red ones are due to the weight of the cylinder, and as a result of see here, we're going to have 2 reactions here. We are going to have 2 reactions here, and of course for that particular location B, since this is a frictionless pin, we're not going to, the way it's been connected to the member, it's not going to produce any reaction. However, the way it's been connected at point C, we will have reactions. So for member ABC, then for member CD, we show C sub Y and C sub X the same magnitude but opposite in direction. On the other side, we make the cut right here. So we are going to have one C sub Y downward acting on this side, and we're going to have a 4 C sub X acting at that location. This is just below the point C on this particular, the continuation of the frame that carries it down to point D. Then at point D, we are going to have D sub X and D sub Y, 2 of them in that direction. Let's look at the problem again. This is very important for you to realize that this 100, that the weight, the 50 times the 50K times 9.81 also being applied here at this location, since the pulling in this direction is going to cause a force right here at that location. So it's very important for you to realize that. That is shown by 50 times 9.81. This is the reaction as a result of the weight of the cylinder. So after showing all that, then we would look at some strategies. We applied equations of equilibrium to member ABC first. We take the summation a moment about point A. And the reason we're doing that because we're trying to eliminate as many forces as possible. We could have taken the summation a moment about point C. However, we would have, in that case, too many unknowns, and it would have been very difficult to solve it. But if you take the summation a moment about point A, we are going to eliminate A sub X, we are going to eliminate A sub Y, we're going to eliminate the C sub X. So we're going to only have C sub y as our only unknown, and that's how we come up with that. If we would have taken the moment about point C, we could have done a similar thing and calculated A sub y in that case. So C sub y from that equation, taking the summation of a moment about point A and set that to 0 as a condition of equilibrium, assuming the counterclockwise direction is positive. We would actually go through that equation, solve for C sub y, and C sub y turned out to be 735.8 Newton. Then we take the summation of forces in the y direction because we already know C sub y, so one of the components of the force in the y direction is known now. The only component in the y direction that's unknown is now A sub y. We could have done this differently by taking the summation of moment about point C and then after calculating one of the unknowns, repeat the same procedure for the other unknowns. So both of them would work. In the case of summation of forces in the y, we set that to 0. One of them is C sub y, and the other two is the 50 and 50, 9.81 Newton. These are the forces that are due to the weight of the cylinder with a string that goes over both of, or the rope that goes over both of the rollers at B and C. As a result, A sub y would be 245 Newton. And then knowing C sub y and A sub y, then we would need to also solve for C sub x and A sub x. We take the summation of forces about x in the x direction, which is this direction. By now you know this is the x direction. This is the y direction. So knowing that summation of forces in the x direction is also 0, C sub x minus A sub x will be 0. So from here, we could not solve for C sub x or A sub x, but we did find a relationship between the two, that C sub x and A sub x, they are equal. So then, now we are going to take a look at a member CD and try to apply the equations of equilibrium to member CD. We take the summation of moment about point D, we set that to 0. As such, we would see that C sub x multiplied by 1.2, remember this is where the force would cause some kind of, it will cause the rotation about that, and I think there's also a typo in this equation. I'm going to correct it because C sub y is also causing that. However, C sub y is known. So we're okay. No, there's no correction. This is correct. For 1 second, I thought there's a problem here, but I don't think so. So C sub x is 1.2 multiplied by 1.2. The magnitude of C sub y is known as 735.8. And we already calculated that from the previous step. It's the opposite direction when it is applied to point C with respect to the free body diagram of A, B, C. So C sub x multiplied by 1.2 plus 50 times 9.81 times 0.7, and this is the moment as a result of the force of the cylinder. The moment arm would be 0.7 meter minus 735.8, which is C sub y, multiplied by 1.6, which is this distance between the location of the application of C sub y and the point in which we would like to take the moment about. As such, C sub x would be 695 Newton. Okay. So, C sub x is 695 Newton. Remember previously that we calculated C sub x to be equal as A sub x. So A sub x would also be 695. So this is A sub x as well. Then summation of forces in y, we set that to 0. As such, d sub y minus 735.8 plus 50 times 9.81 is 0. We set that to 0. As such, d sub y would be 245. Summation of forces in the x is 0, so d sub x minus 695 is 0. D sub x would be 695 Newton. And as I just mentioned, since a sub x and c sub x they were equal, then a sub x would be 695 Newton. That's pretty much the solution to our group problem solving. Let's take a look at our attention quiz. Make sure I have everyone's attention when I am going over these problems. When determining the reactions at joint A, B, and C, what is the minimum number of unknowns for solving this problem? Again, when determining reactions at joints A, here, B, here, and C, what is the minimum number of unknowns for solving this problem? Again, we are after the minimum number of unknowns for solving this problem. Okay. The minimum number of unknowns should be 3 for solving such a problem, since we have 3 equations of equilibrium available to us. For the same problem, above problem, imagine that you have drawn a free body diagram of member AB, this member only. Okay. What will be the easiest way to write an equation involving unknowns at B? A summation of moment about C, we set that to 0. Summation of moment about B, we set that to 0. Summation of moment about A, or summation of forces into X. Let's take a look at that here. We try to eliminate as many unknowns as possible. In that case, it's better if we take the summation of moment about point A and set that to 0. So the correct answer is really C. The reason for that is if you really draw the free body diagram for this particular member, you will see that there's one unknown, F sub BC, at this point. F sub BC, this is supposed to be really B. F sub BC. And there are 2 more unknowns at point A sub Y and A sub X. This is A sub X and this is A sub Y. So in order to solve the equation for less unknowns, for the less number of unknowns, we would simply take the moment about the point A and set that to 0. Okay, so that brings me to the end of the lecture. Let learning continue. Next time we would talk about other related topics. Thank you.